Hello everybody, so my name is Hogan Park. Today we prepare a technology seminar and we will introduce some basic concepts in machine learning. So you may hear a lot about machine learning these days, right? This is the core technology in the recent success of the artificial intelligence. So we'll just give you the brief introduction about the technology, but won't be so difficult. So don't worry about it and just relax and enjoy my lecture. So here's objective. So I would like to give you basics. So in the term machine learning, so you may wonder what is learning and what is the data in some important perspective toward the both the learning and the data. So we will give you the overview about them. So here are two important learning methods in the machine learning. The first one is supervised learning. So what is supervised learning? So we have some guidance, right? So literally it is saying that something is supervised learning. So the supervision is obviously from the data, right? The pair of input and output, right? We use some notations, X and Y for the pairs. So X represents input and Y represents output. And then we learn a function. So here the learning is a goal of machine learning, right? In deep learning. This is what we are interested in, right? When we learn this function, and we can predict the output from any new input. So this is the preparation. So the guidance is from the data available. We learn the function, and then now we are ready for the new test data. So the function is presented here as f, right? F can be anything. So this can be the deep neural network, right? Or simple linear classification model. So the most of the f function, I would say almost everything, they do find decision boundary, particularly for the classification task. So let me give you an example from the perspective of classification. So for the classification, we assume that Y is discrete value. So which means Y could be a cat or a dog or female or male. So it is predefined and it has some discrete value. And the function f is to find the decision boundary. So assume that we have two class labels, for example, dog and cat. And then the decision boundary, there's a function f find the decision boundary in this feature space. For example, some point is here and some point is here. The function f is find this decision boundary. So when new input came in, something like this, so we don't know the class label yet. When the new point is placed in here, and this function predict, oh, this is dog. When new input is placed in here, oh, this is cat. That is the role of the function. Then it's time to think about how to present the new input in this space. So in this example, we're using the two-dimensional input space, right? Which means every image, for example in here, every image, so we have some picture of the dog, right? Sorry, bad picture. So we need to convert this feature to two-dimensional space in some way. For example, we can count how many black pixels, for example, and how many circles. We can count the circle in the picture, and we can count the length of the hair of the object, right? We can count something like, so the number of circle in this picture is 5, for example, and number of triangle, I don't know, number of the length of hair, it was the maximum length of the hair of the object. The animal is, for example, 20 centimeter. This is the two-dimensional representation. And then we can move on to this space, right? 5, 20, and this new input is placed in this place. And then we predict, oh, this is cat. Here is a procedure. So this is what supervised learning do, particularly for the classification. We also have important task. So when y is continuous values, so it is something like predicting the stock price, or predicting the height of the chair, or weight of the people. So y could be continuous value, right? When y is discrete, which means that task is classification. When y is continuous value, we call that task is regression task. So this is the examples of the supervised learnings. And another category of the task is unsupervised learning. So without knowing the y, the output label, without knowing the y, we learn the function to simplify the data. It is to simplify the data. So it is the goal of the unsupervised learning is understand the data. So that is the most important goal. And it could be another input for the supervised learning. So first of all, to understand the data, because unsupervised learning, we simplify the data into the dimensional space and define the important global features. So here's the example. So for example, clustering. So clustering is to find important groups in the data. Think about, we have student data set, many student data set. Without knowing the label, based on the similarity between the record, student data set, we can find some important clusters, right? What the cluster means. Maybe some cluster is from the computer science department, and some data set is from the ECE department, right? But we put the label, but we don't know label yet. But we found the group, and we just understand, oh, there are two big groups, big gatherings in the student data based on their similarity. But we have to define the similarity, right? But similarity could be from their class registration, or birthday, or their membership to some study groups, right? So based on the similarity, we can find some cluster. So without knowing the label, so that is called clustering. So let me give you more examples about this. So matrix factorization. So it is something like dimension reduction. So in reality, think about the student dataset. I'm sorry. In the student dataset, we can imagine many different labels, right? For example, height and weight, their student ID, and the entrance year, their gender, and what else? Their GPA, right? And their scholarship. We can imagine many different information about one student, right? It could be 100, something like that, considering their address, or we can imagine many information, right? But we don't know which feature is important and particularly useful for understanding data or another supervised learning task. So, it is also difficult to get massive number of data set. So to avoid the burden, we reduce dimensionality to lower dimension. So previously we have 10 different features for the student, and we reduce their dimensionality to 2. And then we can visualize their distribution in 2-dimensional space, and then we can find some phenomenon here. For example, there are 2 groups in this space. Before we see the 100 the features, we difficult to see there are 2 features, 2 groups here. But in this low dimensional space, we can observe the important phenomenon, and we can develop some classifier. There are 2 groups, so we can here draw a decision boundary, and we can classify them using this regional information, right? So another thing is representation learning. So let me give you the example later. So we'll give you all the examples in this slide later. So if you don't understand, so don't need to worry about it. So just remember supervised learning. We have the true output, and it could be discrete or continuous. When we don't have the label, the true output, but still we are able to find the clusters and reduce dimension space, and we can find their representation. It is much similar to the matrix factorization. So let me give you example one by one. So let's start with the unsupervised learning. So I told you the clustering is the process of grouping into classes of similar objects. But here class is not the same as the class label. It is just like a grouping a set of objects. But we should define the criteria about the similarity. We need to define how to measure the similarity. When they are similar, it should be important. It should be important to assign the object into the same cluster, which means in this 2-dimensional space, the data are placed in here. When the similarity is based on the distance in the space, and then we put these 2 points are in the same cluster. Obviously, this point is far from this point, right? So they are not assigned in the same cluster. So they are in the different clusters. So to find a cluster, we need to predetermine the concept of similarity. So that is the most important concept in the clustering. And clustering is the most common and frequently important task. So what is the example? So when you go to the Google, you can find some clusters of news articles, right? Because we have so many number of news articles real time, right? Even right now, people writing the new news articles, and when you go to the Naver and Daum portal or Google News or Yahoo News, we have so many number of the news articles available, right? But difficult to watch everything, difficult to read everything. So the machine learning, particularly clustering techniques, helps you to understand what's new in the recent trend and what's hot right now. They cluster, for example, all the Samsung's Galaxy phone information in the one cluster, and they just show the representative one. For example, some based on the view count, and when people see, we did just sort the number of the news articles in the cluster and just pick the hottest one and show the figure and the article. And when you click the full coverage, you can see all the news articles in the cluster. Let's see another cluster. So it is about the computer science. So nothing else. So just one instance is in the cluster. Another cluster here is about the soccer game. So Tottenham in West Ham, they had a game, and Son Heung-min scored, right? That is about one of the clusters. And when you click this, you can see another similar news articles, and this is about the Apple Watch. Similarly, you can see another article. So we have 4 different clusters. So this is from my Google News. What is other application? So from the clustering, and we can find the object, right? Here clustering is based on some pixel color similarity or some boundaries about the object, right? And we found the cluster by looking in the pixel color, right? And when they are similar, we put the same color here. So we have 1, 2, 3, 4, 5, 6, 7, 8. And so when you take the computer vision class or image processing class, and you learn more about this. And in this case, we were able to put some label, right? It is something like the semantic segmentation, but still could be classified as the clustering. So what about the movie data? So when you go to IMDb, some movie database. Also Netflix, so they have many movie information in their database, right? So we reduce their dimensionality into the two-dimensional space, right? Even though they have many information about one movie, right? The actor and director and synopsis and their stories and reviews and people's rating and their budget, right? By looking at all the information available, we reduce the dimensionality into the two-dimensional space. and then we see, oh, here is some cluster, and put some color here, put some color. So we are able to find the clusters, and then we put some label from the human. Oh, when we see the cluster, and most of them are the documentary, or most of them are about the big budget in the exercise or IMAX, right? It is to understand the data. So what about the representation learning? So representation learning is the set of techniques that allows a system to automatically discover the representation. So particularly it would use for feature detection and classification. So without using the raw data, particularly the for example image data set, we don't use every pixel. We reduce the dimensionality into, for example, 10 different float value. We have 10 float value, and then learn the classifier, for example, neural network, and we see the images labeled cat or dog, right? So this is called the representation learning. So this is a really popular technique right now. So particularly the success of the deep neural network is actually from the representation learning. So you heard about GPT, right? Or autoencoder, right? They all to get the representation, the low dimensional representation. It is to understand the relationship about the data, but we don't need to have the actual labels, but still very meaningful to present in all the data set in the low dimension space. It is applicable to many different tasks such as classification and just feature detection. And it is an automatic. So before we have the representation learning, we needed to pick the relevant features manually. So we use the image data set. We have cat, some house here. To understand this is cat or not, before we have this representation learning, we needed to pick some important features, right? So, for example, we can count the number of the red pixels, number of blue pixels, or number of the circles or squares, and we have the feature information 10, 2, 5, and then learn the classifier. But depending on your goal of the classification, the labels of the classification, the effectiveness about the feature will be little different each other. So that's why we needed to have some automatic approach. So in that sense, representation learning is very useful. And computationally or mathematically also very sound, which means we understand the meaning of the float in here. So not in here, so in representation learning. So let me give you the example as well. So the success about the deep neural network to take the image, video, graph, sensor data, all use representation right now. So in this class as well, we will teach about the important advances about the representation learning. So let me give you an example. So we have a social network. So this is called Karate network. So it is about the social connection between the 4 different groups. So each node represents the person, and each edge represents their communication. But our goal is to classify, for example, here gender. So the color is from the actual true label, but in our actual classification task, we just give their genders of the some of them, and then we try to predict the rest of them, right? Oh, sorry. We pretend to know the some of them's label, and in our testing stage, so we try to predict the rest of them. But similarly, so before we had the representation learning, we needed to pick the handcrafted features. But by having the representation learning, we can place their each node into some point in the two-dimensional space, right? Here. So actually, this transformation has been done without knowing the class, any class label. We just use their edge and the relative communication, their patterns, and we are able to find two-dimensional representation, and this actually represents their class labels, right? They're well separated, except some points, but still looks good, right? And we can apply this to the gender classification or religious view classification, something like that. So we have assume that we have 4 label here without knowing label, so we are able to find the representation. So one of the representation learning in the word in the natural language processing is called the word-to-vec. So word-to-vec is quite similar to this one, the previous network. So we have text, but we have sentences, but we have important assumption to read the sentence, right? That the hypothesis is words in the similar context have the similar meanings, right? For example, so in the football game, 손흥민, son, scored a goal in the recent match. We see the son in this context. Son is deeply related to the football, right? Scored, goal, match, they all related. So this is the important hypothesis when we make a sentence or make a speech, right? They all related. So in the similar, so here context is the location, the relative location around the word. So son in football, scored, goal, match have the similar meaning in this sentence, right? So think about this. So we have the assumption. What if we understand all the relationship using the millions of the news articles or billions of news articles, and then we are able to understand the relationship between the word. And we put the relationship in this latent feature space. And for example, son, football, and goal, and match should be placed in here. So what is the benefit about this word representation learning? Here's the example. So in this representation here, the representation is a 3-dimensional representation. We have the woman and queen. But I told you the representation is able to infer the relationship between 2 words, right? in this, the woman has some three-dimensional float value, right? We add some vector, some float value, and then we have some the value. We looked at which word is located in this location, and surprisingly, man was here, and their relationship is defined something like this. We add the same the relationship vector here, we call R. We add it to the queen, and we added this R vector here, and then we are able to find the king. What is their relationship? So they're like a opposite gender relationship, right? Two women, the opposite is the man. For the queen, the opposite is king. They're able to find the semantic relationship, right? We're also able to find the syntactic relationship between big and biggest and smallest. So the learned representation from the word to back could be used for the document classification. So document classification is we have a news article. Our intention is to predict, to determine this article is about the sports news article or the entertainment news article. So to predict the class label, given the sentence, we know the representation in three-dimensional space for each word. For example, wait for the video. In here, 6-dimensional information in the space. So then 6 and 3 are hyperparameters. So to learn the representation, we predefine the size of the representation. So that is in here. So in this case, we defined that the size is D in here, something like this. So here the D was 6. And then now we have a two-dimensional information and using some neural network technique. So let me give you the details about it later. And we're able to find the label. So that was the power of the representation learning of the word to fact. What about the image? So we have the unlabeled image data. For example, downloaded all the available images from the New York Times or Wikipedia, and we learned some representation learning model, and you're able to find the important representation. So they found that in the data we have several representation important patterns. So that is also one example of the representation learning. So by having this, we just see when we have new image data, which is looking at whether the image includes this pixel, this patch like a pattern in here. We just look at here. Oh, what about this? What about this? Oh, he has two eyes in this image, and then we give the information. Oh, this pixel, so we can find this pixel in the image 2 or 5, 3, something like that. And using this information, we can classify the labels of the image. So that is one example about the use case. And we can also, when we understand the representation, we can generate the very realistic images as well, to randomly generate, right? Because we understand the nose and the eye patterns, and in the representation, we can combine randomly the available patterns, and we can generate the realistic photo and the animals and dog. That's called like this. Alright, so it was the brief overview, and let me about the unsupervised learning. So let's move on to supervised learning. So if you have any question, so please come to Q&A board, and also we will have the Q&A session as well. So once again, we have examples. This will supervise the function. It helps to learn a function, right? The function is mapping the input to the label. And this is gonna be used for predicting labels on the new data. Okay. So for the input data, so f is the function, right? The function has the parameter, so learn a function means we learn the parameter about the f. So here's neural network, and the parameter means in this case we have some input, and in neural network we have some scores about the edge, and then we have some activation value, and it is multiplied by the edge, and we have some final prediction probability. And to do that, we need to have some score to the edge. So this is called the parameter. Let me give you more easier example. What is the more fundamental, the easiest example about the parameter? So we can make some linear model about x. Maybe we can imagine this linear classifier. For example, the x can have two float value. For example, 0 or 1. This is feature vector, right? The 0 represents maybe the count of the black pixel or count of the red pixel. And we multiply some the matrix A, and we can get final prediction something like 2 to 1.1. This is probability about the probability about of the being a dog, for example. So given any input, we just multiply this matrix, in this case one dimensional, so vector A, and then we can get some score. We just train, this is called the parameter. So when we have this one, we can get any probability. So we can predict the labels to any new test data set. The X is the new. So A is learned, and after learning, it is fixed. During the learning, it is changing all the time. So the goal is to find the best parameter, best A in this case. The A is most important, right? This is everything about the model. So when we have the best one, we can predict the best result with respect to this Y, right? This is the parameter, theta in here. This is a simplistic example. So now you can see we have several design choices for the supervised learning. So how to represent the function f. And to learn the parameter, we need to tell this is good or bad. When it is good, we don't need to update the data, right? When it is bad, we need to update a lot for the data, right? So we need to decide how to determine the good or bad, right? So usually, the good means our prediction from the learned model is similar to the true label or not. What is the easiest way? Just see the difference, right? The absolute difference could be used for the measure. Another thing is how to find the best parameter theta. So that will be also one of the important questions, right? And I also prepared some recent progresses on machine learning. So I think the most important success these days could be the AlphaGo. So as you know, AlphaGo is able to beat the master Lee Sedol, and we were really surprised at the result because the number of possibility in the Go game is beyond our imagination. So as far as I remember, it is more than 2 to the 30th, right? The more than 30th, the possibilities. It is very massive and impossible to count every the conditions, right? But they did that, and they're using the reinforcement learning techniques. So that is also one of the subfields in the artificial intelligence. So we are able to predict the winning probability when we have some decisions. So we can maximize our winning probability, and we try to react to the Lee Sedol's the action, and we just have the best choice. That is the important success these days. You may heard about the Tesla's self-driving vehicle, right? So they announced the recent version, so beta 5, right? So it is a monthly subscription service. So very easy to see Tesla in the United States. Probably these days in as well, right? So when you see the Tesla, you can see their self-driving functionality. So nowadays they've recognized the light of the front vehicle and the light in the green light of red light at the crossroads, and the people in the sidewalk and the parked cars, and the performance is very impressive, right? And we also have the GPT-3, so sorry for some Koreans, and it is a massive language model. So it learns the language is sequential information, and we can generate our own the sentences in our documents. So you can generate your own novel or your own homework as well. So all the professors are thinking about that seriously. So is it from the artificial intelligence? It will be our near future. So we are very serious about it. So thank you for your attention. So if you have any other questions, let me know. So I'm part of the Learn Data Lab in SKKU Machine Learning and Data Mining Lab. If you're interested in please let me know, and have a wonderful weekend, and I see you soon at some classes. Bye bye.